Welcome. And today we are going to start getting into energy, really focusing on work and power and a little bit about potential energy. So let's get started. So with most new units, we're going to start off with some definitions. And if you have your packet with you, that'll be great. Let my computer get situated here. Okay. So first of all, we're going to talk about work. Now, normally in class, what I would do is have everybody grab a book, a nice heavy book. Here's one for me. And I'd have everybody hold it out with their arms straight. And we'll see how long we can go before anybody drops it. Now, after this is done, we clap and congratulate who's done it. And then we ask the question, have we done any work? In our minds, holding that book up was a lot of work. But the definition of work in physics is that you have to move to do any work. So no distance, no work. So holding that book straight up, that's no work. No work according to physics. And so work is measured in joules, and the equation is pretty straightforward, which is work equals force times distance. And we'll do a couple problems with that. What we want to remember, though, is the equation for force. Take a second. Do you remember what the equation for force is? Yep, you got it. Force equals mass times acceleration. And so most of the time we'll use acceleration of gravity, which is 9.8. Mr. Foss would argue a ton that knowing your units are important. So that bottom yellow part that tells you work is in joules. Force we've done before, but that's a reminder it's in newtons, and distance is in meters. Once again, if you're working in your packet, this is the definition is number 8 on there. So pause if you need to. Now, going along with work is power. And power is the rate at which work is completed or energy transferred. So work and power are very closely related. And this is the definition number 7 on your packet. So power is measured in watts. That's if you talk about light bulbs, you have a 60-watt light and so forth. And this is how much work to do 1 joule of work in 1 second. So when you hear that, you might think, okay, I'm working with joules and seconds. So time has to be in there. And what else has to be in there because we're working with joules? Something from before. Yep. We need work. So power is work divided by time, or power is work over time. And so those work and power are related, and you can find power by finding work and so forth. So the equation itself, P equals W over T, is not too complicated, but we can make it into several different steps. And a reminder, power is in watts, work is in joules, and time is in seconds. So when we do all our problems, when you get to page 2 and 3, we want to remember what our units are. So when I start page 2 and 3, I'm going to probably write those up top to help me out. And obviously the equations, but the equations are on there already. Matter of fact, the units are even on there for you, I think. But if not, put them on there. All right, so let's talk a little bit about energy and then do some problems. Energy is the ability to do work. Pretty straightforward definition. And this is definition number 2 on your packet. So as of right now, or the rest of the day here, you will have number 2, excuse me, we're going to do number 6 also. 2, 6, 7, and 8. So right now you've got 2, 7, and 8. Now there's a couple types of energy, but today we are just going to talk about potential energy, or what we would call stored energy. Now, this is associated with its position or height, if you will. When an archer draws back a bow, it creates that energy pulling back. And this is what we'd call elastic potential energy, energy stored in stretching and compressing. Now, which is good, there is energy there. We're not going to do any calculations with that. The one we're going to do calculations with is when we talk about the height, or gravitational potential energy, or GPE. So GPE depends on both mass and height, and there's our equation with it. So potential energy equals mgh. Well, we know mass is m, and we've talked about g a lot. What is g? You nailed it. 9.8 meters per second squared. That's the gravity of our Earth. And then height is all obviously in meters. We always use meters. So there's our units for it. Those are our 3 equations that we're going to work with. Now, when you're working on your pages 2 and 3 today, you're going to see that they're only actually work and power, and we're not going to get into potential energy, page 4, until the next lecture. But we wanted to put all these together. And as a reminder, energy is always in joules. All right, let's see if we can answer some questions quick. So work is measured in, I know it's not kilograms or seconds. It's either watts or joules. And work is joules. Stored energy is also called, we've talked about all these words, but checking back in my notes, potential energy is stored energy. At which position does a card have most potential energy? Now, when looking at this question, I think a lot of us could say right away, but remember, potential energy is on mass and height. And in this picture, all those people are the same. So they have the same mass, so we don't have to worry about that. So we're just thinking about height. So which one has the highest? Yep, you got it, number 1, or A. Now, once we know that one, this question becomes quite easy. Which one has the least potential energy? Well, it's not the last one, because it's still higher than number 3. Number 3 is the closest to the ground, so it has the least potential energy. So the answer here is C. All right, now let's hit a math question. Now we have all the answers here, but let's go through it. How much work is done when an object is moved with a force of 55 newtons, a distance of 4.0? Now, off the top of my head, I'm looking at this, and what is it asking for? It is asking for work. So the first thing I need to do is remember the work equation, or go find it in my notes. So I know that work equals force times distance. Now, I'm going to look in the problem and see if I have those things. I know I'm looking for work, so that is my variable I'm going to solve for. Do I have a force? I do. And how do I know it? 2 ways. It says force, which is a big hint, but then if it didn't say force, I got those newtons right there. And that will remind us that, hey, force is in newtons. So I'm going to put that in there, 55. Now distance, and again, we've got 2 hints on there. It says distance, and then M is our meters. So we can plug that right in there. So now once we've got that in there, we can put that into our calculator. give you a second to grab your calculator to see what this is. What's that you say? Oh, yeah, I agree. It's 220 joules. So our answer in this one is D. Pretty straightforward question, asking work and giving you both of those. All right, let's step it up just a small notch. Not yet. Question after this one. What is the SI unit for gravitational potential energy? Now, we could go back and look. Remember, energy. I know it's not C or D because that's meters per second. That's speed, and seconds is time. Is it joules or watts? I remember talking about watts with light bulbs. Yep, you got it. It wasn't watts. That's power. It is in joules, A. All right, let's hit another question here. At first look, it looks pretty simple. It's asking for work. This looks like just like what we've done before. This will remind me what I'm going to need to do. And so I'm going to write the work equation before I even read anything else, because that's what I'm going to have to use. Work equals force times distance. How much work must a 35 kilogram dog do to move himself up a hill that is 2.5 meters, ignoring friction? Well, I know I got to solve for W, so I can put that down. And now I'm going to look for force. Is this force 35.0 kilograms? No, force is in newtons, so I don't have it. Here's where we got to remember our other equation. So as you do some problems, you may want to write this down if you forgot it. I can solve for force by knowing the equation force equals mass times acceleration. So I first have to solve for force in this problem. What's my mass? Well, that's the 35.0 kilogram dog. Now, maybe one of the harder problems is, what is the acceleration on this dog? And we think of acceleration going left and right, but a lot of this in our energy, we're going to talk about the acceleration of gravity going down. So we have to remember that the acceleration of gravity is 9.8. All right, now that we've got there, that was the tricky part. We got it. We multiply those together. I'll give you a second to multiply those together. And I got, what did you get? Did you get 343? That's what I got. Now, we're going to take those force, and again, just to remind us, that's in newtons. We're going to take that and plug it back into our original equation we wanted. So now that we solved for force, we just have to put the distance in there. And the problem gives us distance. It's in meters. So 2.50. So at the very end, when we do this, work, I'm going to move over here, work equals 343 times 2.5, and I get 857.5 joules. Final answer. So now some of these problems can get a little tricky because you got to use two equations. Now, as Mr. Foss thinking, could I give you a question with some other stuff in it? Yeah, but this is pretty good thing to find. Maybe to do this, I could give you the acceleration and you have to find the force from that way. But you get the idea of using two equations. Again, the equations aren't very hard, but you got to think through what the units are. All right, let's do one last question, and then you guys can work on page 2 and 3 in your packet, and we'll do some of those questions in class. So if you get stuck on any of them. Here it says, what is the gravitational potential energy? Now, I always stop when I see that because that tells me, what am I looking for? And I remember talking about this. This is our GPE. And this formula is, you can write it a couple different ways, but normally they'll say mass, gravity, and height. It doesn't matter the order because they're all multiplying. But I stopped right there. That's the equation I need to use because that's what it's asking for. All right, let's reread. What is the gravitational potential energy of a 45.10 kilogram ceiling fan that is suspended 4.000 meters above the floor? Well, I know I got to find my potential energy. Do I have the mass in this problem? I know by my units, and that's in the correct units. I didn't try to trick you and put grams. So we can start with that number, 45.10. And help me again, what's G? Ah, that's gravity. That is 9.8. And H is in height. Do we have height? We sure do. And we know that one's in meters. All right, so we have everything here. Let's plug this in, our calculators. And what do we get for our potential energy, gravitational potential energy when we're all done? I get 1,768. We can't leave it like that. I don't know what that is. Is that years or money? That's joules. Now, just a reminder, I'm using 4 sig figs because there are 4 sig figs in the problem. All right, now it'd be wonderful if you would attempt pages 2 and 3. We'll work some of those questions in class on remote week. So see you soon.